Hello everyone, and thank you for joining this webinar. My name is Meven Wiban, and I'm a coastal engineer at DHI Australia. And during this webinar, we will talk about some design principles for coastal developments. A lot of the principles that are going to be detailed today are based on some concepts that have been developed in the two previous webinars. These two webinars are still available online, so I suggest that you have a look at it. The idea of today's webinar is to detail some of the key principles that are required when designing artificial beaches and harbors, for instance. So this is the agenda for today. First, we will detail some of the main principles for artificial beaches. And then we will look at some examples where these principles have been applied in real projects. And then we will have a look at the harbors and some of the principles for the design of the harbor layout. And we will go through a project where this harbor layout has been optimized for diminishing the impact on the coast. Before having a look at the main principles for coastal developments, let's have a look at the concrete example of coastal development. And this is a picture of the state of Monaco, which is located on the Mediterranean coast. It's a very small state enclave within France, which means that it's constrained in its surface. And it's a very popular area, which is very attractive, so it has a very high density of population. It's actually the country with the highest density of population in the world, with about 18,000 inhabitants per square kilometer, which is very, very high, as it can be seen on the picture on the right. And today, the total area of this state is about 202 hectares. But among these 200 hectares, roughly 40 hectares have been gained on water. The map in the bottom left corner shows the evolution of the area in time. So we can see that over the last decades or even century, the overall shape of the country has actually changed quite a lot. In red, we can see the shape of the country in 1861. And we can see that successive developments have been conducted mainly during the 20th century. All these developments consist in different types of areas. Some of the extension are harbors, for instance. There have been some artificial beaches that have been constructed. Some headlands have been added to the shore. Some business areas, a stadium, a lot of things that require some space, and that the Monaco state has gained on water. And in 2006, the state of Monaco has decided to extend even more their land on water. And therefore, they have asked some architects and big construction companies to come with some ideas of design that could be added in the green area, which is located in the center part of the map. This area is about 10 hectares, and basically the architects and construction companies could provide any kind of ideas, and among these ideas, the state would choose the one that they prefer. We can see that a lot of different shapes and concepts are used. So we have a very open layout with some sort of offshore structures. We have a very angular development with a lot of narrow channels. We have some floating islands. We have some crescent-like development. So that's all these are the kind of design that came. And the problem with this development is that they're not really realistic. We can see that some of this development would require some non-existing technology, and some of them would be very difficult to build because it's a very difficult area to work with. It's very, very steep and very rocky. And on top of that, some studies show that some pre-selected design were actually quite harmful for the coast because it would limit the water renewal and it would change the conditions along the beach that are on the coast. So this design were not very much satisfactory. Of course, it's a bit futuristic and it looks nice on pictures, but when it's a matter of constructing it, it can be very difficult and very pricey and very harmful to the neighboring environment. So this is the design that has been selected and which is being constructed right now. So as we can see, this design is very well integrated in the existing landscape. We can nearly not see it. Actually, if we didn't know that it was a drawing, we could not guess that it's added to the actual landscape. So it's very well integrated. It's easier to construct than most of the previous layouts we've seen because it's not located offshore, so it's allows working in a relatively shallow environment, even though in this area it's already 30-40 meters deep and very steep. But it's easier to do, and therefore it's cheaper. And also we can see that the shape of the reclamation area is relatively well streamlined. So some of the studies that we've made showed that it would even increase the water renewal at the beaches which are located close to the extension, and therefore improve the quality of the water at the beach. So all in all, this development has only advantages. And this is a good illustration of some of the principles that we are going to look at afterwards. So basically, we try to have a development that is well integrated in the existing landscape in order to avoid critical or bad impacts on the neighboring environment. So this extension is being constructed at the moment. And then I'm pretty sure that in the next decades, we will completely forget that it's a completely new area or neighborhood. So being careful about the design of development is very important in order to avoid unexpected problems. And we are going to have a look at what it means for the design of artificial beaches. But first, let's have a look at some of the characteristics of the good beaches and coastal lagoons. So these are some pictures of nice beaches around the world. Even one of them is an artificial beach that has been constructed not so long time ago. And the elements that constitute good beaches and coastal lagoons are basically the quality of sand. So we want to have a not too coarse sand. The quality of water. It's important when we go and bath or swim in the water, or when we do some activities in the water, that the quality of water is good and that there are not some pollutant or components that would be harmful to us. The ease of access is also an important parameter because if we want to go on the beach, it has to be accessible to most of the people. We don't want to have to struggle to go to the beach. It's better if it's easy to access on it. The width of the beach is also an important factor because if the beach is too wide, it will take and require a long time to go and swim, for instance. Then the swimming safety and the recreational activities that are available or that we can do in this area are also important. We want to be able to go and swim safely, so avoid rip currents as illustrated in this in the top right picture. And finally, the dunes and flora and fauna around the beach are also something that make a beach a bit better than another. So here are some principles that we use to prepare and design sustainable waterfront developments, and in the case we're interested in today, in artificial beaches. So what we want to have is a stable beach. Basically, we don't want to, it's quite expensive to build an artificial beach from scratch. So we really want to have something that is stable, and to achieve that, we try to have a plan form and a profile for the beach that is in the equilibrium shape and at the equilibrium orientation. Then we would like to have some terminal structures that will help keeping the sand along the beach sections and avoid the sand to move away from the beach. And then, as we've seen in the previous webinar, we would like to have a relatively good exposure, because we've seen that the wave exposure is a very, very important factor to maintain a good quality of sand. And that's something that is important when we design the beach. Obviously, the exposure should not be too large, because if the waves are too strong, it's gonna be dangerous for swimmers. So it's a matter of finding the right balance between too much or not enough waves. But of course, safety should be considered. The beach material is also very important, so we should try to aim at some medium, well-sorted sand, which we can usually find in marine sand or along the coast. And finally, the water quality is also very important, and we should ensure that the flushing of the coastal lagoon is good enough to renew the water and avoid stagnant waters, for instance. So now we will go through some of the principles. So we can see here that we would like to have a stable platform. This is very closely related to the longshore transport that we have detailed in the first and second webinar. So basically, we want to have a beach that is oriented in its equilibrium orientation. So to do that, we have a very useful tool I've been talking about already previously, which is the Q alpha curve. And this is a very useful tool because it will help us finding the equilibrium orientation and see how far we are from this equilibrium orientation. So basically here we have a coastline which is oriented towards 303 degrees north. And this Q alpha curve shows sand transport rates as a function of the orientation. And we can see that the present orientation of the beach is 303, that conduct to a longshore sediment transport of about 15,000 cubic meters per year. And when we design a new beach, we want to reorient or realign the beach in order to face the equilibrium orientation, which is in this case 284 degrees. So that means that in average the sediment transport will be zero along the beach if the orientation is set to this orientation. Of course, the waves are not always coming from the average direction, so we have some variations during the year and from season to season. So we will have some extreme westerly waves that will arise, which will tend to turn the beach counterclockwise in this case, and some extreme northerly waves which will tend to turn the beach in the other direction. So that's why we have to add some additional beach width in order to absorb this natural variability. And all this can be assessed by using the Q alpha curves for a specific stretch of beach. This was for the plan form of the beach, which should be stable, but we also would like to have an equilibrium profile for the beach. If you remember from the previous webinar, we have seen that the shape of the profile is mainly driven by the cross-shore sediment transport, and this is very much linked to episodic storms. So basically during storms, we have acute erosion, which lead to a flattening of the profile, and during the calmer period, we have processes that tend to push back the sediment from the deeper part of the profile towards the upper part of the beach. When we will add some sand to a beach, it will naturally tend to adjust based on the processes. So here we can see, for example, on that picture that we've added, or some sand has been added to the beach, and it has naturally adjusted to the condition and the forcing by becoming very, very steep. So that's something we would like to avoid. And this can be done by putting the sand in as close as possible to its equilibrium shape, and by using sand that is as close as possible to the existing one. So we can avoid this kind of problems by building artificial beaches with an expected equilibrium profile based on the composition of the sand that is used for building the beach. We should also keep in mind that as this is very much related to events, we should add a bit in a similar way than for the platform. We should add some additional beach width in order to absorb the natural variability of the profile. So in order to anticipate what is going to be the equilibrium profile of a beach, we use the DIN profile, which relates the sediment size and the coastal profile. So as we can see on this figure, we have different steepness of profile depending on the grain size or the median grain size. So we can see that for very coarse sand, we have very steep profile, and for finer sands, we have flatter profiles. The quality of the sand that is used for the artificial beaches is very important. Of course, it's important when we work on it. We prefer to work on some finer sand than on a very coarse gravels. But it's also important with regards to the stability of the beach itself. Usually we tend to avoid sand from land sources because the sorting is relatively bad and it's either too coarse or too fine. If, for instance, we have a lot of fines contained in the sand that is used for an artificial beach, as soon as it's placed in the environment, most of the fines will be washed away by the waves, and therefore the volume of the beach will change dramatically, and the shape of the beach will change dramatically. So that's something that has to be considered when selecting the sand for the artificial beach. With regards to the coastal lagoons, one of the key parameters or the key principles is to maintain a good water quality in the lagoon. And to achieve that, we want to have a good flushing of the water from the lagoon, so it's renewed on a regular basis. Usually the water exchange in the coastal lagoon is driven by the tide. In the end, we want to have a sufficiently large opening, so it's a lot of water is getting in, but we don't want to have it too open because we want to maintain a relatively calm environment. So once again, it's a matter of finding the right balance, but in general, when we have large openings, we have better water exchange and therefore an improved quality of water, which is much better when we wanna swim or have some water sport or activities in the lagoon. So we will now have a look at an example where these principles have been applied. And on this map, we can see we have Denmark, and the capital of Denmark, Copenhagen, is located where the red dot is. And in Copenhagen, a new beach has been constructed, which is named Amager Beach Park. Basically, the site is very well protected due to a shallow shore face, and also due to the presence of the neighboring island, which limits the wave action along that beach. So we can see here on the wave rows that the wave height, the significant wave height, is nearly never above 80 centimeters, which is very low. And as we've seen in the previous webinar, the exposure of the beach to the waves drives the quality of the beach. And we can see on these pictures that these conditions led to a very muddy beach, which was unattractive. It's important to note that in front of this beach there were some relatively deep channels where currents was relatively strong. And that is an important thing because it's going to be used for the development. So if we think about the main principles that we've detailed before and how we're going to apply them in this specific case, the beach is moved seawards to get more exposures from the waves and therefore increase the flushing of the fine sediments. The beach has been oriented towards prevailing waves, so two main wave directions from northeast and from southeast. So we can see that the two stretches of the beach have different orientation. Then some terminal structures and headlands have been added in order to maintain the sand in each sediment or in each stretch of the beach. And between the actual land and the new beach, we have a coastal lagoon, which will have a good flushing because it will use some of the currents, that is, some of the strong currents I was mentioning before. And also it has two openings, so it flushes very, very well. Having the coastal lagoon is also a way to minimize the quantity of sand that is required to construct the beach. So instead of having a plain beach with sand everywhere, we simply have a narrow beach which is constructed, and we use the remaining space to construct a lagoon, which is going to be used for recreational activities and also which is protected from the waves, which is good for swimmers, for instance. And this beach has been constructed a couple of years ago now, a bit more than 10 years ago. So far, the beach has been working very well. It's become a very, very popular beach. It's very crowded in summertime when the weather is good in Copenhagen. It's been working very well, so no refill has been necessary so far. And the lagoon is also used a lot for recreational activities, so swimming and kayaking and some other activities, kite surfing, for instance. It has to be noted that this beach was integrated in some long-term development. So, for instance, it's very easy to access from the city center of Copenhagen because there is a metro line that is arriving there. And since this beach has been constructed, the neighborhood has completely changed. It's now becoming one of the most popular neighborhood in town, and it's been growing extremely fast thanks to the presence of this beach, which was not the case before. It was more an unattractive neighborhood. So this beach has completely changed the way this part of Copenhagen is behaving, and yeah, it's now a great asset for the city. This is another example of a project where DHI has been working. So this is located in San Stefano in Alexandria, which is located on the Mediterranean coast of Egypt. And basically in this case, we have a completely opposite situation than the previous project we've been looking at in Denmark, because in this case, we have no beach before the construction of the project. And we have relatively rough conditions, whereas in the previous case, we had not enough wave exposure to maintain a good quality for the beach. So let's see how these conditions have been used for the design of a new artificial beach. And basically what's been done is to search inspiration in nature. What you can see on the picture here is a natural beach located in Portugal. And this shape has inspired the the development and the concept for the new artificial beach, which is detailed on the drawing on the right. So basically, we have an equilibrium bay protected by big structures and with a relatively small opening. So we have the large waves coming from the offshore part, and these waves are diffracted through the entrance of the bay. So we reduce the wave action in the beach along the beach, but we still maintain a little bit of action to ensure a good exposure of the beach. But on the other hand, we manage to reduce quite significantly the wave action. And once again, since we have these structures to maintain the sand in this location, we don't really need to refill the beach, which is also very good. So to successfully design these artificial beaches, it's usually the same procedure that is applied every time. First, it's important to analyze and understand the natural processes. And we usually use numerical models in order to test the design that we imagine for the development and potentially adjust it depending on the modeling results. So it should have an acceptable impact on the neighboring stretches of coast, and also it should obey the setback regulations. In the end, the numerical models are very useful to optimize and check all these points. We've seen that most of the design that we have looked at are using coastal structures. It's important to have in mind that when we design a man-made beach, we will most of the time require some structures to maintain the sand at its location. And if it's designed well, we can see that, for instance, on this picture, which has been taken in Denmark, we can see that some of the structures can actually be quite nice looking and be actually an asset for the beach. So it should not only be seen as a negative thing to use these structures, but because if the design is well done, it can have a positive impact actually. So that was for the artificial beaches. Let's now have a look at the ports. And for the ports, it's a bit different. I will start by going through this example here, which is located in India, where we had this stretch of coast and a harbor has been constructed along that coast. And this is a picture from 2009, so we can see that the shoreline is relatively straight. And after years, this structure has been constructed, and we can see that there is a significant accumulation on the western side of the breakwater and some erosion on the eastern part of the coast. So this was in 2010. So this structure we can see have a significant impact on the shoreline, which continues. This is a picture 2 years later. So we can see that the beach has even more advanced in the water, and that erosion has been continuing on the downdrift side of the structure. And a new structure has been constructed. This is a very typical situation. And we can see that it's the same story that starts again with accumulation along that structure. And it's important when deciding on the design of a harbor to make sure that it will have as little impact as possible on the neighboring or adjacent stretches of coast. And here we have a summary of some of the issues faced by the port. So we can have sedimentation in the navigation channel, or seaweed accumulation in the basin, or wave disturbance in the harbor, and difficult conditions for the ship navigations, for instance. And also when the harbor is constructed, it can cause significant impact, as we've seen before. So accretion on the updrift side and erosion on the downdrift side. We typically distinguish 3 types of harbors, and These three types of harbor have different characteristics. The first one is a single main breakwater port, which works by protecting the basins from the main waves by the use of a usually curved breakwater. Then we have the double breakwater port, which consists in two curved breakwater, and it protects the inner part of the harbor basin by because thanks to the diffractions through the harbor entrance. And sometimes, if the diffraction is not enough, some internal breakwaters can be added. And then we have the offshore breakwater, which is very often used when the harbor is located in a very shallow environment. And this type of port is also interesting because we can, by designing it properly, we can minimize the impact it will have on the coast. And it's also interesting to know that since it's located in deeper water, we avoid sedimentation problem and we minimize the capital dredging of the harbor. So let's start with a single main breakwater. So in this case, we have a situation where the harbor is located on the coast with typical incident wave directions from northwest. And due to these waves, we have a relatively strong current that is going towards east. Usually, this type of structure and this shape of harbor is generating a lot of circulations around the structures. So, as illustrated on the upper current field that results from a numerical model, we can see that there is a large eddy that is generated close to the entrance. This is an example of a double breakwater port, which is located in Malaysia. So as I said before, this type of harbor works by reducing the wave energy in the basin thanks to the diffractions through the harbor entrance. Compared to the previous shape or type of layout that we've looked at, the single breakwater harbor, this kind of shape reduces the circulation currents because it has a more streamlined shape. And usually we tend to put the entrance of this kind of harbor as far as possible from the shallow area in order to limit the low frequency motion in and out of the harbor basin. And finally, we can have a look at the offshore breakwater port. This type of port is composed of usually shore parallel breakwater located in an offshore location along the coast. As we have seen during the webinar about coastal protection against erosion, the two main important parameters for designing this type of port are the length of this breakwater and the location of the breakwater in comparison with surf zone. So if these two parameters are set properly, we can minimize the impact on the coast. However, as we can see on this picture, in this specific case, this very long breakwater has had a significant impact on the coast. So we can see a relatively large accumulation in the shelter of the structure. And we can also see that this has been leading to some sort of erosion south of the structure because we can see that some groins have been added in order to maintain the sand in its location. So now I will talk a little bit about optimization of the port layouts. So as I briefly mentioned before, one of the very important parameters is the width of the surf zone and in comparison with the width of the harbor. So typically when we have small harbors located inside the surf zone, the navigation channels have to be maintained, and very often some reservoirs, sediment reservoirs, are dredged in order to catch the sand before it deposits in the navigation channel. And then the sand has to be bypassed somehow on the other side of the harbor. So this can be done by dredging this sand and disposing it further downdrift. It's important that this sand is reintroduced in the system. some of the harbors, for instance, sell the sand, so they can make very good business out of it. But the problem is that this enhances the erosion of the downdrift stretch of coast. So therefore, it's very important that the sand that is dredged is put back in the system along the coast, so we minimize the impact of the harbor. Then when we have very large harbors that penetrate the entire surf zone and active littoral zone, then there is no way that the sand bypasses naturally the structures. So it completely blocks the sediment transport along the coast, and that's where the impact on the neighboring shoreline is the most important, because absolutely no sand from the updrift location is reaching the downdrift area. So that's a big problem, and in this case the sand has to be moved manually or artificially towards the downdrift area. And this is a sketch of a layout, of double breakwater layout, where we try to minimize the coastal impact of the structure. Once again, it's the idea behind this concept drawing is to have something that is as less intrusive as possible in the natural environment. So to achieve that, we tend to have a smooth alignment of the breakwater with a relatively narrow entrance. So so the currents can more easily pass by the structures. Then we try to have a good connection of the breakwaters to the coastline, so we avoid the sheltered area where accumulation of sand and circulations would occur if it was a too angular shape. And then we maintain the navigation depths by dredging or bypassing the sand that is not able to achieve it naturally. When we talk about bypassing the sediment, there are different ways of doing it. The two main methods are either by using a dredger. Basically, what the dredger does is when the sedimentation in the navigation channel occurs, and when the critical depth for navigation is reached or a bit before, the dredger goes out and dredges some of the sand, and then this sand is put back on the downdrift part of the coast, either by using a fixed pipe or by regular dumping, for instance. Another way of bypassing the sediment is by using large structures, as illustrated on the aerial picture that is shown here. So this is a picture taken in the Gold Coast. So this is the entrance of the Gold Coast Seaway, where we have these two large structures that blocks the littoral drift. And we can see on the southern part that there is a jetty that contains a lot of pumps, and these pumps dredge the sand. So we can see that it's actually much more deep below the jetty, and all the sand that is pumped from this jetty is discharged on the northern side of the structure. So that's another way of bypassing the sediment that would be blocked by the structure. And I will now go through an example where we've optimized a harbor layout that was causing a lot of problems and having a lot of problems with maintaining a decent navigation depth. So we can easily recognize Denmark again. So we are not located on the islands as Copenhagen, but now we're looking at a site which is located on the North Sea, which is called Hvide on the west coast of Denmark. So it's highlighted by the red circle. And this harbor town is located at a tidal inlet on the Sande barrier. And as indicated by the wave rose, which is plotted here, we have a very, very severe wave climate. Nearly 90% of the time we have more than 0.5 meter waves at this location. and it can even reach on a regular basis 4 meters. That leads to a net littoral drift of more than 1 million cubic meters per year towards south. And here is a picture of the old layout of the harbor. So basically we have this town which is located at the inlet. And what has happened is that the first harbor has been constructed some time ago, and this led to erosion and sedimentation problems around the harbor. So in 1963, a new breakwater has been constructed about 400 meters long, and basically this breakwater was blocking most of the sediment transport. So this conducted to an updrift accumulation of a lot of sand, in average 80,000 cubic meters per year. And it's been estimated that this accumulation extends up to 3.5 kilometers north of the breakwater. And as a consequence of this accumulation, the downdrift erosion was very, very large as well, because all this sand that was accumulated along the breakwater is now lacking south of the town. So about 300,000 cubic meters per year were placed along the coast south of the town. So that was the situation before the optimization of the layout, and we can see that we are facing very, very large numbers. And of course, one of the key elements when we're talking about a harbor is the depth of the navigation channel and the access channel. In this area, they had to do a lot of survey in order to investigate whether there was some risk for this for the critical depths for navigation to be reached. And this is an example on the left of one of the surveys where we can see that we have an offshore bar that is progressing towards south, and in a bar that is also progressing and reaching the breakwater. And we can also see that due to this shape, we have eddy forming south of the harbor, which tends to bring sediments in the entrance of the harbor. So with this whole harbor layout, they had a lot of problem maintaining a decent depth, and the natural depth of the bypass bar was 2.5 meters, whereas the navigation depth of 4.5 had to be maintained. So this required a maintenance dredging of about 170,000 cubic meters per year, which is quite a lot. And before optimizing the shape of the layout, we spent quite a lot of time on investigating the coastal processes that we were facing along that coast. We were very lucky because a lot of surveys, bathymetry survey, has been made for more than 50 years. And therefore, it was a very useful, all these were very useful information. And thanks to all this survey, the behavior of the bar has been studied precisely. And this is very important because a lot of sediment transport occur on the bar. So if we understand the way these bars evolve in time, then we can potentially understand where the sediment transport is, and this can be very useful when designing the harbor. And what we found thanks to this analysis is that the bars were following a relatively stable cycle. Here we can see the evolution in time of the distance between the shoreline and the offshore bar, and we can see that it's a relatively consistent behavior that has been identified in these two profiles. So here we can see some of the profiles that have been extracted. So in the black thick line we have the measured profile, and in the dotted line we have the average profile over time. And this behavior that we've detailed before is very easy to see. So we can see that in 1992 the bar is generated, or a bar is present in the profile, and then it slowly moves towards the offshore part of the profile. And in 1996 a second one is generated close to the shore, and this bar will start migrating towards the offshore part as well. we can see that it's not purely linear. So we have some features that appear and disappear from time to time, but this is normal because this is due to the natural variations of the climate, right? It's not consistent all the time. Then, depending on the distance between the bar and the shoreline, we have an increasing depth when we get far from the coastline. So that was a very interesting study and very useful when designing the harbor, because it was important to identify the sediment transport for these different types of profiles. So we've extracted representative single and double barred profile and make some sediment transport calculations with our 1D model in order to assess the ability to bypass sediment in time and depending on the profile. And after this analysis, a morphological model has been set for the project. So this morphological model was based on bathymetry survey that were done in front of the breakwater. So a calibration period has been selected, and this calibration period was featuring a relatively severe storm. As we can see on the top plot, we have a significant wave height of up to 5 meters. So that was very strong wave. And as we can see on the two bathymetry survey before and after the storm, the sandbar has been migrating quite a lot during that storm. So that's what we were aiming at when calibrating the model. Here is an animation of the calibration of the model. So we can see that during the selected storm, we have the bar that is moving towards south. And the model results were pretty good. So what we see here is the measured elevation along the bar. So we can see in black that's before the storm, and in red what has been measured after the storm. So we can see that the bar has been moving towards south quite a lot. And in blue, we can see that the model was performing quite well to reproduce this behavior. Once we've calibrated our model, we're ready to test some potential new design. And this is what DHI has proposed. So basically, the existing breakwater has been slightly extended and curved in order to increase the bypass, and another breakwater has been constructed south of the port in order to have this double breakwater shape that is well streamlined and that will be able to bypass sediment and minimize sedimentation in the channel. Moreover, on top of these structures, we propose to dredge a lot of the sand that had accumulated updrift of the harbor. And the idea behind this capital dredging was to make sure that we have sediment transport on the outer bar. And one of the issues we've had when working with this project is that before the extension of the harbor, the harbor wanted to maintain a navigation depth of 4.5 meters. But during the project, they wanted to increase navigation depth up to 6 meters. And at the same time, they wanted to reduce sedimentation in the access channel. So that changed a bit the conditions that we were looking at. So we have a calibrated model, and we want to try a new design. So what we've done is to select a series of storms that are illustrated here on the wave rows. So we can see it's a very severe wave climate, but that was a trick in order to be able to simulate yearly sediment transport in a shorter period in order to speed up the computational time. On the little drift calculations, we can see the averaged yearly transport in solid lines, and the dotted line is model results. And we can see that on the outer bar, we have very good correlations between the between the artificial wave climate that we're using and the average wave climate. And based on this 55 days climate, we've been simulating the morphological evolution of the bypass bar, because that's what we were aiming at. And we can see that based on the calculations been made, the equilibrium depth of the bypass bar was reaching about 4.5 meter, which was exactly what the Harbour wanted before they realized that they wanted to have a larger navigation depth. So that was pretty interesting, but in the end, as they decided to increase the navigation depth, they still have to conduct some maintenance dredging in order to remove some of the sand, because the bypass bar is not deep enough. And this is a picture of the constructed harbor, which works pretty well now, and the harbor is very happy. The port is very happy with it. So that was it for today. As we've seen in the last example, there's been a lot of modeling involved in the optimization of this harbor layout, and that will be the subject of the next webinar, which will be held on the 6th of September 2018. And during this webinar, we will talk about modeling sediment transport and shoreline evolution. If you have any questions regarding what has been said today and about this principle, feel free to contact me. I'll be happy to answer your question. Now I will spend a bit of time on answering the question that's been asked during the presentation. Thank you very much.